So yeah, I might have to look up some more problems because I only chose 6. So we have a triangle ABC has circumcircle gamma and incenter I. Where's my circumcircle? I need to click more. So I'm going to draw my in-circle. Yeah, I feel like Japan's math Olympiad is easier than I thought compared to how well they do at the IMO. They usually do pretty well. So the in-circle touches AB and AC at D and E. The circumcircle of BEI. Okay, so we're going to need to make some more room here. The circumcircle of BEI, or I could just leave it like that. So P and Q are the intersection points. We want to show that DEPQ is cyclic. So that's P. This is Q. We show that DEPQ is cyclic. So I don't know if you guys want to see the circles or if it how much it matters. Sometimes I like to see the whole circle, but yeah, I don't know if it's necessary here. The circles can also be in the bottom, like that, if you have like a really tall triangle. Which way do you guys like better? The circles are on the bottom or they're on the top? I'll do them on the top. So. Top is better. Yeah. All right. Move the problem over here so you can see it. So is this like the radical axis theorem or something? I'm not sure. This is 2015. So IE is a chord of one circle and ID is a chord of the other circle. So yeah, we should be able to, we can calculate angle BIE and we can calculate angle CID. So PE and DQ are the radical axes that, yeah, so let's see. Yeah, it might be a little tricky to use the radical axis theorem here. Let's see if there's a fifth point. So sometimes when I want to show cyclic quads, like if I can show there's some other fifth point that lies on it, that can be helpful. So ID is equal to IE. So yeah, we know, so ADIE is a kite. So the center, what if I drew the center of the circle? So we don't even know the circle exists yet, but if we did, and that was the center would lie on AI. Maybe extending QE and PD to the circumcircle. Ah, interesting. All right, I will try that. Oh, QE and PD, so not QD and PE. So like that? Is that what you meant? Okay. And then basically we want to show DE is parallel to GH, I think. If we can show DE is parallel to GH, that solves it. I'm going to delete F for now. All right. Yeah, we could show, yeah, AI is perpendicular to GH. That would solve it. Because we know AI is perpendicular to DE. Interesting. Yeah, maybe it's worth labeling this intersection point. I don't know. So that would mean AH is equal to, oh no. Is it true that AI is perpendicular to GH? I would think if that were, oh yeah, no, that could be true. Yeah, I'm sorry. Yeah. Yeah, this is so weird. You have like the circumcircles of BIE and CID. Is that the same as, if we could show F lies on, so I'm thinking, is that the same as saying that F lies on this, the radical axis of these two circles? No. This is tricky. I think, yeah, what if we just try to show that angle QDP is equal to angle QEP? I mean, that's probably the most logical way. So angle QDP is angle QDI. minus angle IDP. Wow, this is hard. Or at least it looks harder than some of the other ones. Yeah. Okay, D, E, P, and Q. Is the circumcircle of ADE tangent to the other two circles? Or are you sure you mean that ADE? So you just mean this circle? Maybe you meant a different circle. I drew a circle just a second ago. There's another circle I drew that you think might have looked tangent? Maybe AQI? Maybe the circumcircle of AQI. But no, those aren't tangent. It's all right. Oh, the circle with center A. Maybe that's tangent. I don't think it is though, because I think, yeah. Yeah, I don't even see like how to begin on this. I feel like we're gonna need another strategy. Let's see. You We wanted to show that PQ is parallel to HG, right? Yep. Oh, we want to show DE is parallel to HT. Yeah, what's the fifth point on that we could have on that circle? Or we could show that ID. I think this is how I think we're supposed to show that ID. Wait a sec. Oh yeah, no, ID and Q aren't collinear. It just looks like it. Yeah, it's hard to draw. But yeah, ID and Q are not necessarily collinear, and IE and P are not collinear. So yeah, you can't just like use power of a point. I mean, one way we could try to do it is we could let D, Q, and EP intersect at a point, and then we could try to show it lies on the radical axis of those two big circles. But I'm not sure how simple that is. We could try to show it has the same power. So BIE, we know angle BIE, we know angle CIB. So angle BIE is one. I think it's 180 minus B over 2. So wait, angle BPI is B over 2? Yeah, that's interesting. Wait, no, that can't be. Oh, no, angle BPE is B over 2. So I think that could be important. Angle BP is B over 2. Let me check that. But that doesn't, that almost doesn't look right. Where's my measurement tool? BPE is 21.5, IBC, no, where did I go wrong? Angle BIE, oh, because that's DIE is not 90 degrees, that's where I went wrong. I'm just doing some scratch work here. 180 minus. Let me just play around with stuff. You guys have any other thoughts? Isn't it half of alpha minus gamma? Do you mean angle BPE? Yeah, no, I think you're right. Yeah. So BPE would be half of alpha minus gamma. Yeah, no, exactly from what you're saying. Yeah, it should be half of, should be what you mentioned. Can you extend PE and QD? Yeah, I think that might be a good idea. GH is parallel to KL. Let's see. Yeah, I think that has to be true by Rhimes' theorem. Like, if the problem is true, then I think GH has to be parallel to KL. And I think they both have to be parallel to DE. Let's see. Yeah, it looks like it. I'll just move it around, but they look pretty parallel. Yeah. Maybe we could use like Pascal's theorem or something. I'm even thinking about using the power ratio lemma. So let's see, are there any other circles that pass through D and E? So DE, I think there's ADIE. Is there another circle that passes through D and E? Not that I know of. Oh, you know what? Let me try something. So we have Yeah, basically we have these two circles passing through D and E, right? So we have ADIE, and we have the N circle. If I can show P and Q have the same, if I can show that if you take the ratio of the power of Q with respect to both circles, and it's the same as the ratio of the power of P with respect to those two circles, then that would solve the problem by the power ratio lemma. Interesting. So now I'm trying a totally new way to do it in my head. So yeah, here's another way to think about it. Oh, really? You can do it by an angle chase? All right. We've kind of gone pretty fast today, so yeah, you can take your time writing out the angle chase. You can calculate angle PQD and angle PED. Okay. So I'm going to delete this circle for a sec, just because we don't know it exists yet. All right. So how do we calculate those two? So PQD is PQG. So yeah, type it out. Yeah, I'm curious. Yeah, no rush because we have plenty of time. We have another hour. So PQD is PQC plus CQD. Okay, I agree with that. Okay, CQD is 180 minus CID, and that's not a hard calculation. I think that's it's like you said, that's half of beta minus alpha or something. Half of alpha minus beta. And angle PQC is PAC. Okay. That makes sense. PAC is PAE, I guess, right? I don't know if that'll be the next step. Yeah, PAC. I think how we would do angle PAC. So maybe that's 180 minus APC minus PCA. Okay. So yeah, CID, that makes sense. So yeah, it's like 180 plus beta over 2 minus alpha over 2. I mean, so beta over 2 plus alpha over 2 is 90 minus gamma over 2. So, but yeah, I'll fill in the details for that later. I'm just saying, how would we do angle PAC? So BEP. BEP is IEP minus DEI. Okay. That makes sense to me. I'm just thinking. Okay, so you said we could calculate PQD and PED. Okay, so we have IEP minus DEI. But I'm still wondering, how do we get PAC? Angle IEP is 180 minus PBI. 180 minus PBC plus IBC. And then, okay, so yeah, I guess IEP 180 minus PBI. But it looks like the idea might be right. Okay, so I'm gonna write this out. All right. I'm gonna delete some of the extra lines we added. Make it clear. Okay, but so I'll fix the calculation once I write it up. But I think the idea is right. So it really is just an angle chase. It's a little bit complicated. Okay, so first I'll calculate angle PQD, as you mentioned. So we have angle PQD is equal to PQC plus PQD, which is plus 180 minus angle CID. Yes, the figure will. You know what? I'm gonna hide part of. Whoops. I'm gonna try this. So, what did I just do? I'm gonna draw just the part of the arc that we want. Yeah, you can draw arcs with GeoGebra, so I'm gonna do that. Where's my arc? Circular arc J I. Whoops. Didn't mean to do that. Circular arc BK, that's one arc. JCM. All right, so I'm going to hide the rest of the circle and just show the arc so it doesn't overlap the solution. There we go. That looks a little weird, doesn't it? Oh well. All right, so let's see. So PQD is PQC plus CQD, and that's PQC plus 180 minus CID. Yeah, we don't need F and G. Good point. That makes things look nicer. Okay. And PQC is PAC. All right. And then CID is BIE plus CIE. And then, but DIE is 180 minus A, so that's and then CIE is 90 minus angle, I'll just write it like this, angle C over 2. Okay. And then I can go on to start calculating the other angle. So PED. So PED is equal to PEI minus PEI, which is equal to PEI minus PAI. And two. Okay. Now for PEI, that's 180 minus PBI. So I can't believe this is really just an angle chase. It looked like it was deeper than that, but I guess not. And PBI is PBC minus IBC. Minus angle A over 2. And PBA is, or wait a sec. No, that's PBC. What am I doing? PEI. PBI is PBC minus IBC. And that's equal to 180 minus angle PAC minus angle B over 2 minus angle A over 2. And then, yeah, some sign is flipped somewhere. Let's see, where did I put the sign? Oh, no, because we wanted to show one of them is 180 minus the other. So we'll just say comparing the two, and then we can show that PQD plus PED is 180. And so that means that PEPQ is cyclic. All right. Thank you very much for that. That was fun. Let's see. Let me just compare these in my head. I wrote this without actually checking, but we would have, this would be B over 2 minus A over 2 once the signs are flipped. Yeah, these two end up equaling. So it really was just an angle chase. All right, I will move on to the next one. This is the last one that I chose, or at least I think it is. And so if we end up solving this one early, then I will look for some more problems. So we have two triangles, PAB and PCD. So I'm going to draw point P. So we have PA is equal to PB. I'm just reading ahead a little. So it's kind of like this. So P, A, and C are collinear in that order, and B, P, and D are collinear. And PA equals PB, and PC equals PD. All right. So we have a circle passing through A and C, and it can be any circle through A and C. And then we have a circle through B and D. And basically these two circles intersect at X and Y. So call that X. Whoops. And call this Y. So there's a lot of flexibility here, right? You have any circle through B and D, and any circle through A and C, as long as those two circles intersect. There's like a lot, yeah, of room for freedom here. We want to show the circumcenter of PXY is the midpoint of the centers of these two. So I'm going to draw those two centers. So center of E and the center of K. And what's a good way to draw it? That looks pretty decent. And then we want to draw the circumcenter of PXY. All right. And we show G is the midpoint of EF. So these three circles, they all share the same radical axis, right? It's a weird problem. Yeah, it's almost like a spiral similarity kind of. So, okay, BA is perpendicular to CD. Yeah, I see that's an angle chase. So yeah, I can see why. But yeah, that's a good observation. BA is perpendicular to CD. I'm not going to. I'll just try to keep that in my mind. I'll draw those two segments. But yeah, it's like we have a spiral similarity, kind of taking one circle to the next, and it's like the middle circle is like halfway. You know what? I wonder if this is just like the gliding principle. I mean, so yeah, I feel like, let's see. Now, what if I drew the midpoints of both of those? So like this. So the question is triangle Y a, actually, never mind. But yeah, PH is parallel to AB, and PI is parallel to CB. Let me think about this a little bit. So yeah, we have triangles BDY, CAX. BD. We know G is on EF. Yeah, because they have the same radical axis. No, good point. Yeah, I'm trying to use spiral similarities. So is YPB similar to YDX? I don't think so. Oh, they don't look similar. Is YGB? Well, I don't think so. Is YG equal to YE? I don't think so. I think that would break symmetry. Yeah. Let's see. YGB is 156. YEX. Yeah. Yeah, it's the perpendicular bisector of XY. So I don't know if you guys have seen, there's something called Kc's theorem that I've used in my videos before. I wonder if we can apply it here. So yeah, I'm going to write it on my paper. See if it gets anywhere. Hold on a sec. I think I have something that might work. I'm just checking it out. Okay, so I'm going to draw in xy. Is PF equal to XE? It looks like it might be. Let's see. My measurement tool. .3, 3.7. No, not necessarily. Maybe there's like another cyclic quadrilateral here. So So yeah, actually, I think we can use the power ratio lemma. Just thinking through it. So the P has the same power with respect to both weights, because PA times PC is equal to PB times PD. So P has the same power with respect to the big circle and the small circle, but it doesn't lie on the radical axis. I think that's because it's like one power is -1 times the other power. But basically, every point on this circumcircle of PXY has to have the same power with respect to both circles. That's interesting. So I don't know if there's that much I can do with that. But I wonder if that like solves the problem. I think it might. I just don't know the right theorem for it. But yeah, if basically, if you can, basically what I'm thinking, if you consider the set of points that have equal powers with respect to both circles, so P is one of those points, but I think if you consider the set of all of them, they form a circle, and the center of that circle is the midpoint of the other two. What theorem works for that? Yeah, so I think I've solved it using Kc's theorem. So I'm going to write it up. So I don't know if you guys have seen Kc's theorem on my channel, but it's really useful. Some people call it linearity of power of a point. There's a couple different names for it. But basically, I'll type it up here. So, or it's also called, I'll call it the Power Theorem of Kc, because there's many different Kc's theorems in geometry. It's kind of unfortunate. But this is the Power Theorem of Kc. So if omega 1 and omega 2 are two circles, and let L be the radical axis, and then let O1 and O2 be the centers of omega 1 and omega 2. So this is a really useful theorem. And yeah, I'm not sure if like Evan Chen has it in his book. I'm sure he has it in some form, but basically, so that's the distance from I'll just write it like this. Have you guys seen this theorem before? It's super useful. I've used it on my channel twice, I think, in the past. But does it look familiar at all? Maybe not. But anyways, you've seen it on my channel, yeah. So if we apply it to this problem, it's not very hard to prove either. But basically, if we use point P in this case, if you look at S1 and so I'll just give a name to the circumcircle PXY. So I'll just call it P1 be the circumcircle of PXY. So then we have the power of P with respect to so S1 passes through A and C. So the power of P with respect to S1 minus the power of P with respect to T1 is equal to PA times I'll just write out Kc first. So that's equal to 2 GE times the distance from P to XY. And so that means if we figure out what those powers are, that means that PA times PC is equal to 2 GE times the distance from P to XY. And then similarly, I'll just rewrite it. So if we take the power of P with respect to S2 minus the power of P with respect to, yeah, why did I even call it P1 and not just T? But that's equal to PB times PD. I'll write that as the next line. But that's 2 FG times the distance from P to xy. And so that means that PB times PD is equal to 2FG times the distance from P to xy. So we're using the fact that they all have the same radical axis here. And then PA equals PB and PC equals PD. And so that means FG is equal to GE. And then FG and E are also collinear. So I'll just write up at the top that so FG is perpendicular to XY and GE perpendicular to XY. So F, G, and E are collinear. That's the portion you mentioned. All right, so we have time for one more problem. We might not be able to finish it, but I'm going to try one more, and I'll end in a little less than half an hour. So does this make sense to everyone? Yeah, this theorem, it's amazing. So yeah, try proving it. All right, so let's find another problem. Let me see. Pick an Olympiad that you guys like. Is there any contest that you guys like? So I have the France Junior Balkan team selection test here. We could do that. Let's see, what's a nice problem? Iranian geometry Olympiad. I think there was one time where I picked a couple problems from that already. So yeah, let's see. Let me check. Since we don't have a huge amount of time left, I could try one that's not super hard. How about this one? This one looks good. All right. I think it was 2015 was here. Just make sure it looks nice when I. All right, I'm not going to go check it up. So we have a triangle ABC. M, N, and K are the midpoints. That's M, N, and this is K. Okay, so then we draw the circles with diameter AC and AB. And suppose that MK and MN intersected at X and Y. I feel like, have I done this problem before on my channel? I'm not even sure. So this is X and that's Y. And then we draw the tangents at x and y to both circles. And they meet at Z, and we want to show ZA is AZ is perpendicular to BC. Kind of interesting, right? So this guy, I'll call it Z. And let's erase some of the extra lines. Hide, 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 hide. I think so, because by the radical axis theorem, yeah. So, yeah, if we can show Zx is equal to Zy, Z has the same power with respect to both circles. So that means Za and D are collinear. So yeah, really it's the same as showing Zx equals Zy. And is that trivial? Because let's see, because xk is half of AB and km is half of AC. So xm is equal to my, and I think it's trivial. I didn't even think that xa and y lie on a line, but basically we have mxz and myz are both 90 degrees, right? And not only that, mx has to equal my because xk is half of AB and mk is half of AC. So that proves it. Should I even write that up, or you guys want me to? I'll try to find another problem. That's too easy. Let's see. Let's find another problem. Let's go back. That was supposed to be medium, but we solved it very fast. Guess we'll need like an advanced. It's a good one. This looks like it's probably easy. Okay, I'll try that Olympiad. So I know it starts with a Z. I've seen it before. It's like, is it like Kazakhstan? Oh yeah, here it is, Kazakhstan. It looks a little complicated. This is kind of interesting. I'll just try this one. Yeah, it's weird. My computer's time is off from the actual time by 7 minutes, so I have to keep adjusting it in my head. Okay, so what year was it? I'm just going to add the year just so people can find it. This was 2017. Okay, 2017 one. Oops. All right, so it's GEO to Cobb, 2017. So ABC is a scalene triangle. We draw the circumcircle, orthocenter, and midpoint. Okay, so all right, now I'm going to use my triangle center trick. So that's the orthocenter. M is the midpoint of, oh man, it's of AB. Well, I'll just do this. So I'll call that A, B, and C. All right. M is the midpoint of AB. P and Q are on arc AB not containing C, so this should be angle. Angle ACP is equal to angle BCQ. So here's kind of how I usually like to do that. There's my angle bisector. So basically they're isogonal, right? Well, actually I could just do it this way, because if that's true, then we could draw the parallel. Whoops. So we can basically call this P and that Q. So angle ACP is equal to angle BCQ. So they have to intercept equal arcs. R and S are the altitudes from H to CQ and CP. Okay, that's interesting. I'll relabel them R and S. Yeah, I wish there was like an altitude tool in GeoGebra, but you have to draw the perpendicular line and then do all this. So that's S. Prove that PQRS are cyclic with center M. Okay, that's interesting. So it's clear that MP is equal to MQ since PQ is parallel to AB. It's just showing, but S, I mean, if you do a homothety, yeah, like if you dilate, so H is the midpoint of CE, right? H is the midpoint of CE and D is the midpoint of HF. I wonder if that like helps solve it. Why is H the midpoint of CE? Or C, oh, yeah, no, H isn't necessarily the midpoint of CD. It's my bad. So yeah, we know HSCR is cyclic. I mean, basically this circle has diameter CH, and we know a lot about that circle, right? It passes through, I mean, basically we have that AH and G are collinear and that IH and B are collinear, right? So yeah, we have this circle passing through 6 points. It looks a lot like Pascal's theorem, doesn't it? So we want to show M is the center of that circle. And we, of course, we know M is the center of AIGB, right? From an angle chase. So yeah, an angle chase, yeah, we could show angle CQP is angle CSR, because angle CSR is equal to angle CHR, which and CHR is CQE. So yeah, they're cyclic, and then we have to show M is the center, and M lies on the perpendicular bisector of PQ by symmetry. And so, is there another? Can we show M lies on the perpendicular bisector of RS? So that's the same as saying that RS is parallel to IG. And I think that's probably just an angle chase to show RS is parallel to IG. Should be. Yeah, that's where the condition comes into play. Okay, so we solved this one fast too. Do you want me to write out the solution or go through another one? We're just flying through it. We have 10 minutes left. I'll write out the solution just for the viewers. Okay, so we have angle ACP equals angle BCQ, means that arc AP is equal to arc BQ, which means that AB is parallel to PC. We're speed running GEO. Yeah, we got through a lot today. So whoops. And so then that means yeah, so first we were showing PQRS is cyclic. And that really is just an angle chase. So it's PQ. Yeah, PQ. You are correct there. And so that really, I mean, I'll just say angle HSC equals angle, I think it was HIC. Angle HGC is equal to angle HRC is equal to 90. That means HSI CGR is cyclic. And AIB is equal to angle AGB is equal to 90. So that means AIGB is cyclic with center M. And so now we can do basically an angle chase. So angle R angle RSC is equal to angle RHC, which is equal to angle RQE. So angle RSC is equal to angle RHC, which is 90 minus angle QCE is equal to angle RQP. So that means RSPQ is cyclic. And then since PQ is parallel to AB, then we have MP equals MQ. And then also, we can show RS is parallel to IG. So basically, yeah, since MI is equal to MG, if RS is parallel, so yeah, I'll just prove that here, but basically we have angle, hold on, angle RIG is equal to angle RCG is equal to, trying to remember what this is. RIG is RCG is ICS. And ICS is IRS. Hey, I didn't even have to put dollar signs. So that means that IG is parallel to RS. And if that's true, then I mean, it seems clear to me. So I'll write it like this. So M lies on the common perpendicular bisector of IG and RS. And so that means M is the circumcenter of RSPQ. We can even get, let's try to fit in one more problem before the time's up. We are definitely speed running here. All right. So one more before 1 p.m. in my country. All right. What is a good one? This is a lot of information, I feel like. We'll just try this really quickly. I forgot the name of the contest. I'll just say same contest 2019, I think it was. Just have to put enter so that it comes out nice when I click OK. There we go. Just going to copy it. All right. What the heck? Whatever. Same contest. Triangle ABC is given. That's weird. This contest likes to put C at the top. So we have the median CM. it intersects this circumcircle at N. Where's my and P and Q are on CA and CB, such that PM is parallel to BN. Okay, so this almost looks like a rectangle, but it's not. There we go. Oops. Then we have to, yeah, I doubt we're going to solve this in time. So these are those 2 points. So PY and QX are both tangent. Is it number 3 after all? Let's see if I can just draw the problem. So PM is, so this is P, and this is Q. So X and Y are on PM and QM, such that, wait, how do we know? Are they saying, are they just telling us that QD is tangent? I guess I'm confused. Oops. Wait, what? The problem doesn't even make sense to me. X is on PM such that, oh no, it makes sense. So basically this is X right there. And then this is Y. Wow, this is a hard question, or looks hard. And Z is the intersection of PY and QX. So this guy right here is Z. And we want to show that MXZY is cyclic, but it doesn't look cyclic. MXZY isn't cyclic. Right, triangle ABC. P and Q. The PM is parallel to BN, QM is parallel to AN. X is on PM such that QX is tangent and PY is tangent. Z is the intersection of PY and QX. Huh. You guys see anything I did wrong? It could be a typo that, like, the problem. Let's see. Maybe it was, yeah, I don't know. Do you guys know where I went wrong here? I don't see it. Anyways, it's about time to stop. It's about 1 p.m. in my country, so we've been doing it for 3 hours, but we got through a lot of problems today, so thank you both for participating. So I'm going to stop recording, but for those watching on YouTube, thanks for watching, and have a nice day. See you.